This is the 11 o'clock news with Elizabeth Davis and Chuck Pennington. And special correspondent, me!
Breaking news. Researchers have just discovered an effective approach to describing enzyme kinetics. Graphical representations of this new technique are now available.
We've got the exclusive details on this unique and easy to understand way to describe how enzymes and ligands bind. Justin is on the scene with Alex, researcher at Butler University, and his lab assistant Sam.
Thanks, Elizabeth. Biochemists have long studied enzymes, proteins that catalyze chemical reactions. These proteins catalyze reactions by binding substrates at their active site, a specific portion of the protein structure. I'm really excited to speak with Alex Scatchard. He's recently found a new approach to describing enzyme activity, specifically with hormone receptor relationships.
Yeah, Justin, good to see you. And thanks for talking with me and Sam here. We've specifically been looking at the receptor-ligand relationship because of its similarity with the way enzymes and substrates usually bind.
That's right. When you examine the equation, we see that R plus L produces RL, the receptor-ligand compound. This is very similar to the E plus S reaction that yields ES. Both the reactions are equilibrium equations.
If these reactions are in equilibrium, how do you describe the constants?
Well, we use the formula Ka equals K1 over K negative 1, which these are the two rate constants for the forward and reverse reactions, to describe the way that an enzyme binds to its substrate. Since the units are kind of tricky, we often look at Kd, which is equal to 1 over Ka.
So where does the graphing technique come in?
Well, with enzyme-substrate reactions, we can look at various aspects of the reaction by looking at the graph produced when you plot initial velocity versus time.
That's correct. With our new method, the Scatchard analysis, named after me, we can quantify the receptor-ligand relationship, especially when we talk about hormones.
Can you give me an idea of the variables involved in this graphing technique?
Take a look at this graph. The x-axis measures the concentration of receptor-ligand complex. The y-axis measures the concentration of receptor-ligand complex over the concentration of free ligand. When you plot the points, the slope is negative 1 over Kd. Since Kd measures the affinity of the receptor-ligand interaction, the slope of this line is extraordinarily useful to describe how strong this relationship is. That x-intercept you see is Bmax, which measures the number of unoccupied sites, which is the concentration of receptor.
Seems pretty clear, right? For most of the interactions we've observed, the Kd for hormones are usually in a range of 10 to the negative 9th or 10 to the negative 11th molar.
Wow, that's a really tight bind. Great work, Alex and Sam. Thanks for talking with us today. So what are the limitations of this graphing technique? Let's head back to the studio and discuss.
Thanks, Justin. Well, after looking more closely at this graphing technique, some problems have come up.
That's right, Chuck. Scatchard analysis works with simple models, that's for sure. In a simple case, like the receptor-ligand interaction described by Alex and Sam, it's great. However, if allosteric binding occurs, it's no longer valid. The complexity of such a receptor-ligand interaction cannot be simplified to work with this formula. The plots deviate from linearity.
And that's not something you want to see in a graph of enzyme kinetics, that's for sure. Well, that's all for us tonight. Thanks to our special correspondent, Justin, the now world-renowned researcher, Alex Scatchard, and his lab assistant, Sam. From the Butler News team, have a good night and stay classy, Dr. J.